Hello everyone, welcome to my PhD proposal presentation. First, I want to thank my supervisor, Professor Xavier Maldak, and the respected juries for giving me the time to present my proposal presentation here today. The title of this presentation is Aerial Inspection of Complex Structures Using Multimodal Procedures and Data Processing. This presentation involves 6 sections: introduction, project definition, related works, methodology, preliminary works, and project planning. The first section is introduction. In past decades, industry surrounded us with large structures that most of them depend on each other to function properly. The operational safety, production costs, and capacity of the industrial sites depend on their continuous operation. So inspection and assessment of systems are essential for early detection of any problem, possibly with minimum interruption in the operation, which can be addressed by non-destructive testing solutions. Professor Maldak defines NDT as the testing method for inspection of specimens to detect possible discontinuities, defects, and any changes in characteristics without any destruction or disruption of its serviceability. Here, we have some of the benefits presented by non-destructive testing solutions. For example, cost and time reduction, increasing profits, maintaining quality level, providing better production design, ensuring product integrity and reliability, monitoring the manufacturing process, avoiding failures, accidents, and saving human lives. Also, ensuring customer satisfaction. Thermography is the process of acquisition and processing of thermal information collected by a thermal imaging system. The inspection of industrial components can be done by observing the component's radiation pattern and identifying possible faults and problematic components by searching for any distortion or any unexplainable abnormality in the thermal image. Thermography can be categorized into two different approaches: active thermography and passive thermography. In active thermography, an energy source must produce enough emission to differentiate the region of interest and the background. Passive thermography, on the other hand, is applicable in the scenarios where the region of interest has a lower or higher temperature than the background. Active thermography has two different observation setups: reflective mode and transmission mode. In reflective mode, thermal camera and the stimulation units are placed on the same side of the specimen. And in transmission mode, on the other hand, the thermal camera and the stimulation unit are placed on the opposite side of the specimen. There are three inspection configurations in active thermography: point inspection, line inspection, and surface inspection. In point and line inspection, it's very time-consuming process, but it provides a normal and good temperature distribution. But surface inspection is a very fast method. However, it's almost impossible to provide a normal and smooth temperature distribution. There are 4 types of active thermography: pulse thermography, step heating, locked-in thermography, and vibrothermography. In pulse thermography, the specimen is stimulated by pulse heat. Step heating is similar to the PT method, although the pulse heatings are much longer. And in locked-in thermography, we use a periodically modulated heat to excite the specimen surface. In vibrothermography, we use mechanical vibration in order to generate enough heating that we can detect defects inside the specimen. Drone-enabled inspection can be an alternative to the conventional inspection we have, So here we investigate different areas that drone-based inspection can be beneficial. For example, the first one is growth rate and size of inspection area. Companies expanded their production capacities and built new infrastructures to meet the demands and obtain more market share. There are two examples we mentioned here. First, inspection of PV power stations. Production capacity almost reached 178 gigawatt worldwide, and with a growth rate of 45%. So that most of them are large PV plants. So inspection of these PV plants are very time consuming and it needs lots of resources. Another example is inspection of Canadian roads, for example. So in 2011, National Highway Systems length almost reached 38,000 kilometers. So because the inspection of the roads are really can increase the driver's safety, it's very important to do this regularly and with the time with a actually reasonable time and cost. So it's safe to say that drone-based inspection can increase the coverage of the inspection. Another area is inspection of remote and inaccessible location. So in many cases, the infrastructures are in high altitude places or difficult to access areas. There are three problems that we're facing in this kind of inspection. First, transferring of equipment and human resources. Also, there's always possibility of damage to equipment and injuries for the personnel. And the third one is requiring specific equipment for inspection. So we can conclude that drone-based inspection can increase accessibility. Regarding hard to reach or dangerous sites, working in an environment with existing hazardous chemical components can be very dangerous for the inspectors. Also for inspection of structures like bridge, wind turbines, inspectors need to access difficult locations requiring specific equipment. For example, Hydro-Quebec used aerial platforms instead of helicopters for inspection of transmission lines. Also, another study used aerial platform for inspection of nuclear power stations. So we can summarize that drone-based inspection can increase safety of the procedure. Also, there's another area that inspection using manned aircraft. So manned aircraft often used as an alternative way for inspection of industrial sites. However, to compare to drone-based inspection, manned aircrafts are much larger than drones. Also, they are not operatable in confined environment. Their operational cost is much higher than drone, and finally, using drones are less risky without endangering the staff safety and well-being. So, same as before, drones can increase the safety of the inspection. The last one is inspection of large area or specimen. So conventional methods usually choose two different approaches for inspection of large areas, using multiple inspectors or using multiple data collection sessions. In the first approach, inspectors must use multiple data collection sessions to cover a large area. Also, all the results need to be documented by the different inspectors in different locations, which can cause data inconsistency. In the second approach, inspectors need to set up the equipment in different positions and repeat the calibration, which can cause human mistake and increase inspection time. Besides all of that, locating the identified defects in respect to the whole structure can be very challenging. So it's safe to say that drone-based inspection can increase the safety and increase the data consistency in industrial inspection. Beside all the benefits of the drones, so drones themselves can impose some challenges and limitations. We list some of them here. For example, the effect of vibration and sudden motions in the collected data. Limitation in flight time. There's always been a need for trained pilot to operate the drone. Limitation in pilot. The vulnerability to weather changes, and the effect of drones propellers in the the collected data. So aerial inspections has some challenges. Some of them are listed here: time frame, distance, and propeller's effect. Regarding the time frame, shadow, daylight, and solar radiation can have negative impact on the distribution of the temperature. For example, one study suggests that the best time to do the inspection of buildings are after daylight in order to avoid the impact of solar heating. Many studies actually study a suitable distance or altitude from the object in various applications. The studies also investigate different factors that can affect this distance. We list some of them here. Objectives of the mission. So, for example, one study suggests that 1 meter distance is the optimal one for a small scale crack detection in concretes. Another factor is attached sensors, their quality, and the nature of the sensor. So, for example, one study used Kinect sensor for data collection of buildings. So they had to use 3 to 4 meters in order to collect reliable depth data. Inspection time is another factor. When you want to inspect a large area, you have to increase the distance or altitude of the drone in order to be able to cover more areas in short amount of time because of the limitation in flight time. And the last factor is safety measure. There's always possibility of collision. So the drone's turbulence created by the drone's propellers can unstabilize the flight and drag the drone toward the nearby surfaces. The last factor and the last item we want to discuss here is the effect of propellers. Drones' propellers create wind while operating. The airflow intensity depends on factors like engine power, payload, or weather condition. The wind and resultant airflow can disturb temperature distribution in the specimen surface. The next section is project definition. In this study, we have three different aims. First, we want to address the challenges of the drone-based inspection. We also want to develop a platform for fusion, analysis, and further processing of multi-sensory data. And finally, we want to develop techniques using multi-sensory data for automating the detection of defects and providing advanced analysis of the abnormalities. For the first aim of this study, we have four main goals. First, we want to solve the issue of reflection in aerial thermal footage. Second, we want to investigate the effect of drones' propellers on close-range inspection. We also want to develop thermal image stabilization method for aerial inspection. And finally, we want to solve the issue of motion blurriness by detection and reduction of this effect. For the second aim of this study, we want to develop a multimodal platform, and also we will develop a data fusion engine for multimodal data processing. And finally, we develop a dynamic processing pipeline for automating the process. It's worth mentioning that all of these goals in this aim are software solutions that we will use it for fulfilling the objectives defined in the scope of this project. The third aim of this study is developing a novel technique to generate unwrapped thermal map using multimodal data. And also we develop a method for abnormality classification for aerial inspection. And also we want to investigate the correlation between thermal and phase array UT data for severity estimation of thickness loss. Before going further, we want to go through some of the related works that related to the scope of this study. For this proposal, we totally reviewed around 129 articles, books, and technical reports. In these figures, we show the distribution of these resources based on their publication date and the scope of their research. AIAA organization defines a UAV as an aircraft that does not carry any operator on board. However, a pilot on the ground can control the drone. But in this case, we call the device remotely piloted vehicle or RPV. Many studies categorize drone in different groups based on different factors. For example, U.S. Army roadmap categorize drones into 5 groups based on their size, their weight, their maximum altitude, and their airspeed. Another study used only weight as the categorization factor. And also another study used wingspan and weight as the categorization study and categorized the drone into 6 groups. Here you can see some of the UAV categorization and the popular design that can be categorized under each group. Aerial inspection has many applications. Here we review some of these applications and the studies in that area. The first one is inspection of PV power systems. Quality assurance of PV modules is an essential factor for keeping them reliable for a long time, maximizing the financial and energy returns. One study investigated the feasibility of using aerial inspection for PV plants by comparing module level and aerial inspection in order to see whether the aerial inspection can be beneficial. Also, we have one example of aerial inspection of PV plants here that is conducted in South Brazil for damage detection without interruption the power generation. The studies in this area actually investigate different issues and they provide some solution for it. For example, regarding camera mounting, the studies suggest that the best position for camera is the vertical aim, yeah. And another issue is reflection of the drone. So the studies suggest that minimum flight altitude should be more than 5 meters. Regarding weather condition, the studies suggest that the inspection should be conducted in a sunny, cloudless, and bright day with a wind speed that is not reach more than 4 meter per second. And also we have time of inspection that most of them suggest different studies suggest different kind of time frame for it. Another area is inspection of electrical power lines. So different companies conducted different, actually proposed different solutions for this kind of inspection. Currently, most of the companies use helicopter as in order to inspect transmission lines, but companies are motivated to use aerial platform as an alternative way to do the inspection. For example, in China, they propose a multi-platform aerial system and a modulated communication system in order to inspect the transmission line in a faster way. Also, Hydro-Quebec, that is located in Quebec, actually introduced a line drone platform that used LiDAR and a camera to inspect the transmission lines. KEPCO Research Institution in South Korea inspect the steel towers and the transmission lines using drones, and they use thermal and visible cameras to do so. Weather leak detection. The inspection of buried pipes can effectively avoid water loss and resources. Since leaking water causes temperature differences in the surrounding area of the pipe, the use of thermal cameras to detect the areas that potentially demonstrate water leaks is worth investigating. So one study in Libya actually investigated the feasibility of using drones for detection of water leak, and the result was significant. There are many other areas that can be categorized in inspection of construction and industrial sites. For example, road inspection, building inspection, wind turbine inspection, or bridge inspection. In road inspection, most studies focus on sinkhole detection and also crack detection. For building inspection, most of the studies are focused on moisture detection and heat leak mapping. For example, in Turkey, they use drones for mapping heat loss in suburb area. In Spain, also, they use UAVs for automatically inspect the buildings. Uh, Regarding wind turbine inspection, the studies focus mostly on the detection of defects on turbine surface, and some studies investigate the influential factors for rotor blades inspection. Most of the studies conducted in the inspection of bridge mostly focused on 3D thermal modeling of the bridge and also crack detection. Multisensory system is another area that is related to the scope of this project. Extensive information about the environment and targeted specimen can assist inspectors provide a more comprehensive analysis. It also can cover the limitation of the sensors and make the results and analyses more accurate. So the multisensory system can be help us in different areas that we are mentioning some of them here. Sensor limitation. All the sensors have some sort of limitation based on their nature. For example, visible cameras can be affected by poor illumination and shadows. Thermal camera has a lack of texture pattern and also unreliable object boundary. For depth camera, we can mention lack of texture pattern. As an example, we can mention one study that focused on inspection of road surfaces. After their investigation, they find out dark areas, tire marks, oil spills, and shadows can cause data misinterpretation. So they propose to use visible and depth data to improve the performance of the inspection. Another area is requiring extensive information and data inconsistency. Combination of sensory data can assist us drive new information which can be used for post-analysis. In various cases, companies require to use different sensors to fulfill the requirements requested by the customer. Therefore, they need to collect data with different sensors to provide a multi-layer presentation of the targeted area. So one study actually focused on automatic creation of 3D thermal models. So in that study, they concluded that for inspection of large and complex environment, using thermal image as the only data source is not sufficient enough. Managing sessions and data alignment can cause errors and increase the complexity of the project. So multimodal systems can solve this problem since the alignment is during the data collection phase. And last one is data misinterpretation and data ambiguity. So the combination of multi-sensors can help systems remove the failures and ambiguities caused by sensor degradation and expand the available information regarding the environment by integrating multi-sensors. The next section is methodology. In this study, following research areas are involved: embedded systems, software engineering, unmanned aerial vehicles, thermography and NDT, computer vision, and machine learning. So regarding data acquisition, we will use 4 different approaches. We customize experimental setups, online datasets obtained via collaboration. For example, one of the collaboration we have is with Cranfield University, and also real industrial inspection. Thanks to Torngas, we have access to the real scenarios and real inspections that we use it in our study with the customer's permission, of course. Beside thermal camera, we use 3 different equipments like drone, depth sensor, and embedded system. For the drone, we use DJI Matrix 600 Pro. That is a heavy lifting drone capable of carrying 6 kilogram payload. Also, we use Intel RealSense data sensor that has a depth range of 6 meters. And also we use DJI Manifold 2C as an embedded system that can actually provide the computational power for real-time data processing. Here you can see the development setup that we use in this experiment for accessing the telemetry data and simulated environment. We connect the workstation directly to the drone. Also, the embedded system connected directly to the sensors and the drone during the experiments, and it communicate with the workstation using Wi-Fi. Here you can see the port map that we use for connecting the A3 flight controller to the workstation or the embedded system. One of the software solutions on multi-sensory platform. So the targeted platform is planned to be used in data collection process. It has two main components, mounting platform and embedded system. So the embedded system has following features: synchronized data collection, telemetry data collection, data recording, and Wi-Fi data streaming. For the mounting platform, actually, we will install the embedded system on top of the drone, and this multi-sensory platform will be installed under the drone using the stabilizer we are designing currently in the Torngak company. Another software solution is dynamic processing pipeline. So actually this software will integrate all the processing components that we are using in this study. It has two main entity, pipeline and a step. So we will implement different method, different algorithm, and we can use them as the processing step. The processing pipelines are the inspection pipelines that we are intended to automate. So the system can feed the pipeline and visualize and record the results automatically, and the user can configure the pipelines using configuration files. So the amount of implementation will be minimal. Here, for the first aim, you can see the dataset and experiments, the candidate dataset and experiments we are going to use. And also in the table, you can see the associated objectives for each of these experiments or datasets. In the proposal, also we put this business process models that show us the steps that we need to take for fulfilling each of the objectives, and when we can expect some results or publication during this process. It can clarify the process and help us for time management. For this third aim of this study, also we listed the candidate dataset and experiments here and the related objectives for each of them. Also, you can see the business process flow, same as the first aim of this study. One of the objectives of this study is unwrapping thermal maps. But why it's beneficial and why we need that? So the analysis solely based on thermal image does not consider spatial and geometric characteristics of the specimen. So the best solution is, instead of using 2D thermal image, we use 3D thermal models. But there are some problems. For example, many reliable and well-known methods for analysis of thermal maps are based on 2D thermal images. Also, time and space complexity of 3D thermal model analysis are higher comparing to the 2D thermal images. And finally, industries are resistant to change their procedures because of their standards and many other factors. So the best way is actually converting the 3D thermal models to 2D thermal images in a way that we can maintain the spatial and geometric characteristics of the specimen. How we want to do that? First, we want to collect thermal and depth data. Then we fuse these two type of data to create the 3D thermal model. And then we unwrap the 3D thermal model using UV unwrapping or surface flattening approaches in order to create the 2D thermal map. And then we also visualize the result. Another aim of this study is abnormality classification. So surface artifacts like corrosion, stain, and dirt can cause temperature distortion, which can lead to data misinterpretation during post-analysis in a remote inspection. So how we want to do that? We want to use thermal and RGB images. So we fuse these two type of images, then we detect the hotspot and abnormalities in thermal images. We extract the associated regions in the RGB images, then we classify those regions to explainable abnormality and unexplainable abnormality. How we want to classify them? We use a trained model. For training the model, we collect many different texture samples. Also, we use some online texture data sets. Then we label them, we train the model, and if the result was significant, we can use it as a proven proven method. Another aim is thickness loss severity estimation. But why we need this? So conventional methods like ultrasonic are costly and time consuming, especially for inspection of large specimens. Regarding attaching of the ultrasonic to the drones, despite the advancements in drone industry, close range inspection using drone still impose many challenges as explained before. So how we want to do that? First, we need to actually create a correlation model between thermal image and the phase array UT data. So for doing so, we are collecting different samples with different plates, with different materials. So we collect phase array data and thermal data. We align them. We detect the areas with thickness loss and how much is the thickness loss actually, and then we try to train a model, a correlation model based on these data, and if actually it proven to be significant, and so we can use this model on the thermal images collected by a drone to see whether we can use it as a standard approach for this kind of inspection. The next section is preliminary and current works. During past year, we actually taken 2 courses and we published few papers. So 2 of them are published already. 2 of those are accepted and we are in the process of presenting them. And 1 of them are waiting for customer permission to be submitted in the journal. One of the activities we had in the last year was reflection detection and reduction. The main focus of this research is to propose a method for the inspection of large specimens containing supplementary information regarding the reflection effect to assist inspectors and consequently ensure more accurate and reliable reports and analysis. So this actually method is based on what is happening in conventional methods. So the inspectors collect data from different field of view in order to make sure the detected abnormalities are not caused by the reflection effect. We adopted this idea and use it for automating this process. We used 3 assumptions in this study in order to focus more on the reflection detection and reduction part. First is the aerial thermal images are collected from a certain distance that presents enough landmarks for the matching process. The images should not have local distortion or any non-rigid deformation that causes a mismatch between consecutive frames. Also, there is no moving object or local motion that are not related to the camera movements or existing reflection effect. Here you can see the algorithm based on the published paper. So there are 3 phases: pre-processing step, matching and registration step, and blending and reflection detection. So for evaluating this method, we used three different experiments. The first experiment was based on an online dataset that had images from a lake and surrounding beaches. The reflection of sun was appearing in the images. We used it for the first experiment. The second experiment was inspection of airplanes wing, more specifically Boeing 737. So this actually experiment conducted in a collaboration with Cranfield University. And the third experiment was inspection of solar panel conducted by SenseFly company. So the other activity was thermal stream stabilizer and its application in gas leak detection. So the whole idea is we want to investigate the use of processing techniques to stabilize the aerial thermal footages for inspecting the specimens that need a drone to hover over the object for a while. Okay, so how actually we want to use it for gas leak detection. We propose an algorithm based on analysis of thermal optical flow in order to detect the origin of the gas leak and also the areas with the maximum gas emission. Yeah, for doing so, we conducted an experiment for testing the gas leak detection. So we use an isolated environment involving containers filled with liquids like alcohol and gasoline and other materials. Then thermal footages of the vaporized liquid pushed out of the container, and we record the thermal images during the process. Other activity was the experiments we conducted in the scope of drone-based inspection. So we did these experiments to be used in three different objectives. So first objective was reducing the effect of motion blurriness, stabilization of thermal footages, and investigating the effect of drones propellers in drone-enabled close-range active thermography. We actually conducted two experiments. The first one was thermal footage of the plates placed on the ground was recorded using a thermal camera while two heating sources aim at the plates. The thermal camera was moved constantly during the data collection to simulate the drone's movement. Another experiment was same as the first experiment, but we use a drone to actually conduct the experiment. We used two different specimens placed with internal defects, and also we used airplanes part to as part of the experiment also. Here you can see the experimental setup and also the specimen we use for the inspection, and some of the thermal samples here you can see in the below. Okay, so as you can see, we have some footage showing how we conduct the experiment. At the left, you can see the thermal image of the specimen, and at the right, you can see the drone. We conduct the experiments in different altitudes. You can see we record the data from different altitude in order to use the data for different purposes. Another activity was severity estimation of thickness loss. So we are in the process of collecting different phased array and thermal data in order to be used for for the objective mentioned here, severity estimation of thickness loss. Okay, so the next section is project planning. Here you can see the current progress of the courses, milestones, and the objectives of this study. Also, we have the time distribution based on the defined aims of this study. We can see which aim we focus on in each year. Okay, here you can see a Gantt chart that shows the schedule for the milestones, the objectives, and other part of this project. Yes. Okay, first I want to thanks my supervisor, Professor Xavier Maldak, for his supervision and enormous help that he offered during the last year. Also, I want to thanks on duty program, especially Dr. Clemente, because of his support. Also, I want to specially thanks Torngat Company and Dr. Fernando Lopez because of his advices, his help, and all the activities we did during the last year. Okay.